Welcome to session 2 of the Nonlinear Least Squares Estimator lecture. So let's look at a different approach to nonlinear least squares. And this is an approach that Stata will use when it can. And I think it is its approach that it naturally embeds in its nonlinear least squares estimators. And it's using a Taylor series approximation rather than using our kind of brute force optimization of this function, as we might think of doing by using Newton-Raphson or other such strategy. And here's essentially how it works. If we have our variable y expressed as a function h of our variables x and parameters and our error term, this is our kind of setup for nonlinear least squares. And you can think of this as in the parameter space, where we have plotted here the two dimensions, right, of our theta 1 and theta 2. For a given data set, we're trying to find that combination of theta 1 and theta 2 that minimizes the least squares. And here's just a section of that curve, of that surface. And at any given point, if we look close enough, we're going to be able to approximate that region by just a kind of flat square. You think of just laying a flat square against the surface, and right up close to that point, it's kind of a approximation. And so here's how we do that. We take a first order Taylor series approximation. So here is our h, and we at any theta, we evaluate it at theta naught. Add to that the first derivative of h with respect to theta, evaluate at theta naught times theta minus theta naught. And then we have the error here, which is the rest of the Taylor series that goes on infinitely long. And if we denote the derivative here, the first derivative, as simply d sub theta h at theta naught, and we drop out the error term, and therefore we turn the equal into just an approximation, we get h of x and theta is approximately h of x at theta naught plus the derivative of h, the first derivative, times theta minus the first derivative times theta naught. Notice we've got theta minus theta naught, so we take that and it just kind of goes through. Okay. Now, if we do some clever defining terms here, and we will call our derivative just simply x naught, and our h we will call h naught. Then I can rewrite it and say that y is h naught minus x naught times theta naught plus x naught times theta plus my error term. And if I wanted to keep the residual in there to just actually state what it actually is equal to, we've got the total error. Now, if we define a y naught equal to y minus the h naught plus the h naught times theta naught, then we can restate the whole thing as y naught is equal to x naught transpose theta plus this error term. And that also looks like a regression type function, but now it looks like a linear one. And the question is can we use OLS? And we can. Again, it'll work out fine if the error terms are independent and there doesn't exist strong collinearity in the derivatives. This is a kind of an approximate. Now, the only problem we have is that y naught itself, which is part of an h naught, which is a parameter, is parameterized, and we don't know theta naught, and x is also a function of the parameters, as well as our theta naught here is the parameter. So clearly we can't just run a regression on this because we don't have this in the data set. But the solution to this in its kind of basic form is the X transpose. If you remember, if we were to get a OLS estimator, it's going to be X transpose X inverse X transpose Y. Take that and come down, and we've got our X transpose X inverse X transpose Y. And just create an algorithm out of that. Plug in a starting point for theta, our parameters to be estimated, and that will give you another theta, right? That's the solution for this theta. Take that theta and plug it back in, and you get another theta. And you just keep iterating this. And what you end up with is a method called iterated reweighted least squares. And this has the same properties that the nonlinear least squares estimator if we were just to use the usual approaches to maximization. And so this is not a bad approach, and it goes a lot faster, actually, as long as you can get these written up, these quantities, in terms of the equations above, written up and calculated. This can be a lot faster than a brute force algorithm that's going to, again, use something like the Newton-Raphson to be able to find the maximum. That's not to say that you can't use a Newton-Raphson. It's an optimizing algorithm as long as the parameters are maximums are in the interior of the parameter space. But this will go a lot faster, and if you wanted to have some fun, you could program a least squares approach in Stata using a Newton-Raphson algorithm, and then just compare it to this approach that Stata would typically use, and you will find that this one will go a lot faster. But it may not be a good solution in the sense that did it actually arrive at the solution that you would consider good. So one way to check this is that we look at our function of y in terms of its Taylor series approximation, y as the h, the derivative, and this theta hat minus theta naught, which we call theta star, and then I've got our residual over here. And again, we have our residual of y minus h is equal to our theta naught, theta star plus r. And applying our OLS type algorithm again to this, we have theta star is equal to x transpose x inverse x transpose u. But this should be u. I mean, this should be 0, right? For two reasons. One is the independence, but also you consider that this theta star itself, since theta hat, it's being a consistent estimator, converges to theta naught, this quantity goes to 0, right? So this theta star really actually should be 0, which means that if you were to use this with your final solution, calculate these quantities, calculate h and x naught at the final solution that you got from your algorithm above, and then run this regression of this u, essentially, on x naught, the parameter estimate that you get from that in terms of theta star should be essentially 0. And as a matter of rules of thumb, as opposed to statistical testing, you could say, is this t statistic really small, like 10 to the negative 4, and is the r squared really small, like 10 to the negative 8? What's also interesting to note here is that the variance of this estimator is actually still the variance of the theta hat estimator, right? So because again, it's going to be the variance of this, and that's going to be the variance associated with the theta hat, because this is a constant over here. So the variance can be easily arrived at by looking at the mean squared error of this regression. So essentially we have sigma hat squared is the mean squared error of that regression. This is one way to kind of quickly estimate and then to quickly evaluate whether you've actually stopped at a good point. You didn't end up on some wrong spot is that this should be roughly 0. And you can get a quick estimate of the covariance matrix of your estimators as well. Now, in terms of the finite samples rather than asymptotically, this linearization approach, which is only using the first order term, right? It's only just putting a let's see, what do we do here? Sorry for the delay, but at the moment my drawing instrument is not working. I seem to be running out of. There we go. Wow, I don't know why that happened. All right, so we're just using this first order term, and it was put in like a two-dimensional flat sheet on the surface. And for small samples, the bias can end up being large, variance can be too small, and the parameter is not actually normally distributed. So how do we check this? Well, one way to do it is to use a bootstrapping technique in which we have a model of y in terms of our h at the estimated values. And we draw from our error terms. So in other words, the error term is, or the residual actually I should say, from this model, because we're already putting in the estimated values, so we're getting our residuals here. We'll have an empirical distribution. And this is what you draw from. So you're going to draw a set of values. You will then, so let's say, draw k values, and then you will generate a set of y's. So we have our set here of the model now for each of those draws, and then you do nonlinear least squares on h, right? So you would, essentially k is going to equal to your sample size here, and you would draw, and you would save that, and repeat it, do it over and over again. Then you would get a set of bootstrapped estimates for theta hat. Now, actually, what I should have done, I think, given my notation, I should have let this be n, and n for sample size. And the alternative is to say I'm drawing a vector E from the residuals, and I've got k vectors, and then I am going to do k of these analysis, at which point I don't repeat back up. The idea is you want to draw a set of residuals, and typically you do that with replacement from the set of residuals, and draw the same number of residuals as you have in your sample. And then you generate your new y by the equation where you have this already calculated, and you are going to add these residuals to it. Then you run your nonlinear least squares estimator again, and you get your estimates, and you save them for the number of bootstrap draws that you did. So let's say that the mean of all of the estimates that you got, we'll call that theta bootstrap bar. The sigma squared bootstrap is the variance, actual sample variance across the number k here is going to be the number of times you do this bootstrap estimator. And so we just get the sample average, where we use 1 over k, not 1 over k minus 1. And we can create a skewness statistic, which will be the square root of k, the summation of k times this quantity squared, summation times that quantity squared, and then take the 3/2 of that, take the ratio, and that's going to give you skewness. And this term is going to give you kurtosis, which is a 4th power, and then the denominator is the sum of the squared and then squared. I'm going to switch color. I don't know if it's the color that's causing trouble. Probably not. It definitely is not. It's quitting on me. Now, with these in hand, you can actually test for normality by testing whether the skewness is appropriate for the normal, which would be 0, and whether kurtosis is appropriate for the normal. And these two statistics will have this distribution. Normal 0, 6 over k, and the normal 0, 24 over k. Or an easier way to do it is just simply use the SK test in Stata, and that will give you a skewness and kurtosis test separately, as well as the joint test of the two for overall normality. So that would be a way of testing normality. You can also look at the percent bias. Define that as the mean of the Bootstrap samples minus the actual estimate divided by the actual estimate times 100. And you notice that you can look also at how the mean of the Bootstrap sample is different from the estimate using this scaling of the variance of the nonlinear least squares estimated divided by k to the 1/2, and this statistic is a normal 0,1 approximately. So you can actually test the question of bias as well. Variance, you can look again at the percent of excess variance, and that's essentially taking the Bootstrap variance minus the estimated variance divided by the estimated variance times 100. You can create a statistic that is k times the Bootstrap variance divided by the estimated variance, and that's approximately chi-squared k minus 1 degrees of freedom. Or you can use a statistic which is z times w, which here's w up here, minus the square root of z at k minus 1 minus 1, and that is a normal 0, 1. And you can use that to test the statistics as well. And then finally, and this is not actually z, I thought I had that wrong. Let me redo this a little bit. And do this a little bit. What I really mean here is actually 2. So this statistic is a normal 0, 1, and you can use that as a test of overinflated variance as well. And something not to forget here is that asymptotically we had our go back here, this is a capital sigma, the capital 1, the covariance matrix. We have our theta hat converging to a particular distribution that's normal and has a covariance matrix. I'm just going to call it sigma. At which point we have that the sigma hat divided by the standard error of sigma hat is a normal 0, 1. Okay. We are using a consistent estimate of sigma and not the actual sigma, right? So we're not using the actual up here. Switch to color. This is based, the asymptotics are based on the actual covariance. We are not. We are using think of it as a hat over the estimate. We're doing the estimated quantity here. And this ratio need not be normal, even though sigma hat has gone to a normal. And our asymptotic distribution would presume with the actual variance in there, we would get a normal 0, 1. So this is important to remember because when you are evaluating your estimator, it's not necessarily sufficient to simply look at a Bootstrap distribution of your theta hats and ask, is that normal? You really want to look at the test statistic, the t-statistic that you're using, and see if that is normal, because if the variance term has not converged sufficiently close to its appropriate term, it doesn't necessarily have to be normal, and this is the one that's going to be of concern with our testing. So there's three ways of doing that. One is a fully non-parametric bootstrap, and that means you're going to bootstrap the full data and then rerun the analysis. So unlike what we did above, where we were just bootstrapping the sample of the residuals, here you're going to bootstrap the whole data. You've got to be careful that you use a bootstrapping strategy that's faithful to the data generating process. But if you can't do that, then you can bootstrap the data and just re-estimate the model and keep doing this over a number of times. And then you can use that distribution of these beta hats in order to evaluate the distribution. So you could look at the t-statistic, which is your beta hat divided by your standard error hat. And you bootstrap this statistic, and that should be approximately normal. And if you're happy with that, or even not, even if it's not normal, you can just use the confidence interval that is based on the distribution of the beta hats that you estimated. So even if it is highly skewed, you can get the 0.025 percentile and the 0.975 percentile. And that is an empirical bootstrapped confidence interval. If you want to test, you can base a test on the center on the null. So you can shift that distribution over to the null, and you can use that as a test. Semi-parametric is what I was mentioning above. You estimate the beta from the full data, and then you bootstrap the residuals. And you generate the y values, again, based on the bootstrapped residuals, and then get your estimates, and you redo that. And again, in this case, you can, if you want to test, if you can embed the null in your function being estimated. So you can actually take your function, and you've got theta hat for most of it, but for those points that you want to test with something 0, you substitute in the actual value of 0, or the 0 that you're trying to estimate. And then you can get your residuals and bootstrap the residuals, rerun the analysis. So you're basing it on a constrained model with the null. Use the full model if you're interested in confidence intervals. You can use a fully parametric one, and this is where you estimate beta hat and the error, and then you essentially draw from the distribution of the errors, and this is where you assume a distribution of the errors. And again, the null model versus the full model, depending on whether you're testing or doing a confidence interval. Easiest one to do is the non-parametric, so long as you can properly bootstrap the data. Not necessarily the most efficient one, because of course you're adding kind of extra information here when you use these ones, right? This one you're going to add information about what the distribution is. You're going to assume a particular distribution. Now, as far as the asymptotic test then, the nonlinear least squares estimator really has the same tests as OLS and GLS. We have kind of the list of tests, walled statistics, ring multiplier tests. You can do weighted least squares. You can do model specification tests. You can do tests that can do comparisons across models. For example, there is the J-test, which is what I have here as follows. The J-test is that you estimate your function under one model, and you estimate your function under another model. So this is 0 and 1, model 1, 0 and 1. And then you run a regression of y on these estimates, which is the estimate of your model 0 on the difference between the two models, because since you estimated, you can get the difference between the two models. And a test that this alpha is equal to 0 is a test of H not, the zero model of H. So that's one way to test the across models. Another way, and this is the one that I actually like, is Clarke's test. It's based on a very simple logic, and it's also similar to Vong's test. They're not identical, but they have a similar type of a logic associated with them. And how that works is you have your two models. Your hypothesis is, let's say, that model 1 is the same as model 2. You actually can do one-tailed tests as well, but for the moment, look at the logic of the model 1 is equal to model 2. If that's true, so they do equally well in the population, then for any given sample, the error term associated with each model, one will be just as likely to be better than the other, or the reverse. In other words, the probability that the squared error under model 1 is greater than under model 2 is 0.5. And so we simply do a sign test of these squared errors. So you take essentially the probability of the error from the one model squared minus the error of the second model is greater than 0 at 0.5 as kind of a underlying hypothesis that they're equal to each other. And if you were to find a variable as being equal to, just a dummy variable as being 1 if in fact it's greater than, and 0 if this difference is less than, then this variable, 0 and 1, is Bernoulli 0.5. So if you go across the whole sample size, the sum of those Bernoulli is a binomial sample size at 0.5 when H naught. So based on this expected number for D, you get a distribution of this sum. If this were a binomial distribution, then this statistic has a particular distribution associated with it, and you can base your test on how extreme the observed sum of D is compared to this model here. And this is really what a sign test does, so you can do this in Stata by just typing sign test. And you can put in the residuals squared. And this really is in my experience, a very nice test. These do not have to be nested models. This is what's nice about it. They don't have to be nested models. It's also the same type of test that we use for comparing models in maximum likelihood as well. Clarke's test can be done that way as well, only it's using the likelihood rather than the squared errors. So if you look up Clarke's test, and it is in the readings, you will get a fairly clear picture on how to use them. Notice that if the two models have a different number of parameters, then there is an adjustment to calculating the statistic, and his papers that I've given you in the readings will tell you what that adjustment is for the different number of parameters in the models. So this ends session 2 of the Nonlinear Least Squares lecture, and next we'll go on to looking at considerations such as measurement error and what impact does that have on the estimator.